Identifying the interval on which the function is increasing or decreasing, find the function local and absolute extreme values. This information can be obtained from the first derivative. If the first derivative is positive, then the function is increasing. If the first derivative is negative, then the function is decreasing. If the graph increases and then decreases, then the function attains a local maximum. If the graph decreases and then increases, then the function f attains a local minimum. And so all of these can be found from the first derivative, specifically the sign of the first derivative, positive or negative. We then find the first derivative. This is the product, so we would have to use the product rule. The derivative of x squared minus 3 is 2x times the second factor plus, we keep the first factor, x squared minus 3 times the derivative of the second factor, which is e to the x. We then set this equal to 0 and find the critical points. To solve this equation, we use factoring. First, we factor out e to the x. If it is 2x e to the x and we factor out e to the x, then we end up with 2x. If it is x squared minus 3 times e to the x and we factor out e to the x, then we end up with x squared minus 3. Inside the parentheses is a quadratic e to the x, x squared plus 2x minus 3 equals 0. And so we can factor it further. E to the x times x plus 3 times x minus 1. We should check it. X times x is x squared. X times negative 1 is negative 1x. 3 times x is 3x. 3x minus 1x is 2x. And 3 times negative 1 is negative 3. This is a zero product because the product is 0. So we can set each of the product equal to 0 and solve for x. E to the x equals 0, x plus 3 equals 0, and x minus 1 equals 0. E to the x is an exponential function, so it will never be 0. There is no solution for the first equation, e to the x equals 0. For the second equation, x plus 3 equals 0, so x equals negative 3. And then for the third equation, x equals 1. And so we found 2 zeros for the first derivative. These 2 values are called the critical points. They are also used at cut points. We use the 2 points or 2x value to cut the number line negative infinity to 3 intervals, cut at negative 3 and cut at x equals 1. We then check the sign of each of these subinterval. Keep in mind that this is the sign of the first derivative, and these are the only zeros that we found. There is no other zeros. Because these are the only zeros, we only need to check the sign of one test point in each interval to determine the sign of the entire subinterval. Between negative infinity to negative 3, we can use any number in there, x equals negative 4, for example. Between negative 3 and 1, we can choose x equals 0, and more than 1, we can choose 1,000, 1,000. Why not choose small numbers? Any number in each interval. And then we check the sign of the first derivative at the test points. At prime of negative 4 is, it is easier to use the factor form of the first derivative to test the sign of the first derivative. At prime of negative 4 is e to the negative 4 times negative 4 plus 3 times negative 4 minus 1. Remember that we are only interested in the sign of the first derivative, not the actual number. E to the negative 4 is a positive number. Negative 4 plus 3 is a negative number. Negative 4 minus 1 is a negative number. So the product of a positive negative and a negative is positive. For the second interval, f prime of 0 is e to the 0 times 0 plus 3 times 0 minus 1. E to the 0 is positive, 0 plus 3 is positive, and 0 minus 1 is negative, and so this product is negative. Lastly, f prime of 2 is e to the 2 power times 2 plus 3 times 2 minus 1. This is a positive times a positive times a positive, and so it is positive. The sign of the first derivative at each test point determines the sign of the entire subinterval. We have the number line with the cut point negative 3 and 1. This is the number line that goes from negative infinity to positive infinity. In the first subinterval, we check that f prime is positive, and so f prime is positive on the entire subinterval. F prime of 0 is negative, and so f prime is negative on the entire subinterval. F prime of 2 is positive, and so f prime is positive on the entire subinterval. From this sign chart, we see that the function f is increasing, and then decreasing, and then increasing. That is, the function f increases from negative infinity to negative 3, and then decreases from negative 3 to 1, and then increases from 1 to infinity. We conclude that the function f is increasing on the interval negative infinity to negative 3 union with 1 to infinity, and it is decreasing on the interval negative 3 to 1. We use open interval. Since the function is increasing and decreasing at x equals 3, we say that f has a local maximum at x equals negative 3. F has a local minimum at x equals 1. To find the local maximum and the local minimum value, we would need to plug these into the given function. The given function is f of x equals x squared minus 3 times e to the x. And so f of negative 3 is negative 3 squared minus 3, the whole quantity, times e to the negative 3. This is 9 minus 3 is 6 e to the negative 3, or 6 over e cubed. This is the local maximum value. F of 1 is 1 squared minus 3 times e to the 1, which is minus 2e. And this minus 2e is the local minimum value.